Okay, in this opportunity we are going to discuss about the entropy because an entropy is the other factor along with enthalpy that is responsible for controlling the spontaneity of processes. Doesn't matter if they are chemical processes or physical processes, both together, enthalpy and entropy will be responsible for the likelihood that that process will occur. So if we are talking about entropy then, what is entropy? So simply put, entropy is a thermodynamic function, okay? And pretty much what it is used to is to describe quantitatively assign a number to the how many possible ways in which you can arrange a system. In a different way, you can also say that entropy has to do with how many different ways you can disperse energy through a system. So let's put it this way. Entropy has to do with how many different ways to disperse energy. So the more ways you have to disperse energy means that system has a higher entropy, and pretty much it has a greater likelihood that the process will occur. If you go to a more disorganized state, so to speak, then the entropy of that system will increase. Okay, so usually the entropy will have units of joule per mole. So pretty much same as the enthalpy. And we have an equation here. This is, let me rewrite that equation. So the entropy is equal to a constant K times the natural logarithm of W. Okay, and let's say this is capital W to make a distinction from the work function that you may have remembered from thermochemistry. And if you don't remember, there is no problem at all. Okay? But here, K is a constant. Don't worry about the constant. It's a fixed value, so not much information that you can extract from it. But W is a representation of those equivalent ways in which you can have that system. Okay? Now, here, random systems require less energy than other systems. So what does that mean? If we go to the opening slide, what do you see here? Okay. Well, I don't know if your childhood had to do with Legos or no. In my case, I did play with Legos when I was a kid. But this is a completely disorganized drawer of Legos. And that, let me tell you something, that's the most stable form of that system. I mean, you don't even have to put an effort in making the Legos look like that. But think about how long and how much effort you have to put that to build something out of those Legos and keep it in the drawer in a very well organized manner. It takes time, it takes energy. It's not a favorable situation for that system. Favorable in terms of it won't be spontaneous. I mean, if you throw the Legos at the drawer, they will scatter all around the drawer. That's the most stable representation of that system, and that is what that system will tend to do. Okay, so in another example that we can use, I mean, if you have small children, well, the small children are the living representation of entropy. Some people might even say chaos. Okay, so it takes very little effort for these kids to, I mean, make a mess of a room, for example, and it takes a lot more effort to clean everything up to a pristine state. So picking everything from the floor, cleaning everything, that takes more effort. So naturally, the system, if you have an organized room and then you let your kids in that room, the system will naturally flow to a disorganized state. Okay, so that's basically what the second law of thermodynamics will tell you. So systems will tend to go from a state of lower entropy to a state of higher entropy. Why? Because at a higher entropy level, you have more ways to dissipate that energy. I mean, that part I'm already including the chemical component, so to speak. Okay? So, for example, if we go to chemistry, what does a disorganized system means? What is, when we refer to ways to dissipate energy, how do we do that? So look at this situation. You have salt that is dissolving in water. Initially what you have a crystal of salt, right? So it's a very organized structure. You have alternating ions, opposite ions for that matter, right? So you have an alternating pattern of positive and negative ions that form that crystalline structure. When you're dissolving in water, then water starts to getting in between those particles and starts separating the particles, and they are moving in a way. So those particles are not, by particles I mean the ions in this crystal structure, they are not touching each other. Now they are surrounded by water. They are in a more chaotic state, if you will. Chaotic from the point of view of comparing a perfect crystal with now all those ions scattered through the solution. So this is a more disorganized state. Okay, so disorganized state versus organized. Okay, so it takes less energy to go to the disorganized state. Okay, it's just going to be practically spontaneous. So in this particular case, the entropy, because you are going to a higher entropic state, the process will be more favorable. Okay? Additionally, if you have, in this case, evaporation of water, okay, you have all the molecules of water here close to each other. They are interacting with each other. Okay? When you go to the gas phase, now those molecules are moving a lot faster. Okay, remember, the main difference between gas phase and liquid phase is that there is a huge amount of space between the molecules in the gas phase that you have in the liquid phase. And in the liquid phase, the molecules are interacting with each other. In the gas phase, they are not. So ways in which you can dissipate energy in the gas phase is a lot more, requires it's a more disorganized state. Okay, you have more ways to dissipate energy. And technically, more ways to dissipate energy. Okay? That also comes from the fact that to get to the gas phase, you have to provide these molecules with a higher energy level. So you are providing energy to the liquid phase, and then in order to dissipate that energy that you're being providing to the liquid phase, they go into the gas phase, so that now that energy is being dissipated. Now, one of the things that we have to remember from thermochemistry is that we have the first law of thermodynamics, correct? And the first law of thermodynamics tells you that the energy of the universe, the changing energy of the universe is zero, which means the energy of the universe is constant, okay? However, the way you can picture the possibility of transfer of energy is by using this artifact in which we are saying that the changing energy of the universe would be equal to the changing energy of the system and the changing energy of the surroundings. That's just to oversimplify what the universe is. I mean, the universe could be as big or as small as you want it, and then the system and the surroundings are just two compartments within that universe that you are studying. Okay? However, if you set your universe correctly, then the transfer of energy occurs only between the system and the surroundings. That's what allows for the transfer of energy between compartments within the universe. But the changing energy within the universe is zero. Okay, so this is a critical thing to remember. Okay, the changing energy of the universe is zero. That's the first law of thermodynamics. Now, what happens with the second law? The second law is telling you we have a similar expression here. The changing entropy of the universe would be equal to the changing entropy of the system plus the changing entropy of the surroundings. Now, there is nothing that says the changing entropy of the universe has to be zero. It could be zero, but most likely this is larger. Let me erase this. It's going to be larger than zero. Now, this is how that will depend on how you define that universe, okay? But in order to be spontaneous, okay, it could be zero, it could be larger than zero, it could be less than zero, but if the case is that the changing energy of the universe is positive, then you are in presence of spontaneous process, okay? Likewise, if the process is non-spontaneous, then the changing entropy of the universe is less than zero. And if the changing entropy is zero, then it's equilibrium. Okay? So reversible processes, like what you have at equilibrium, then the changing entropy is zero. And spontaneous processes, the entropy has to be positive. If the entropy is not positive, if you are not going to a more disorganized state, that process will not occur spontaneously. So that's the main thing here. Spontaneity has to do with in how many different ways you can dissipate energy for a given system. Okay? Now, if it just so happens, we are focusing on the on the universe right now, but you can separate those entropies, right? You have the entropy of the system. Let me erase that. Entropy of the system and entropy of the surroundings, okay? Remember, for the process to be spontaneous, the changing entropy of the universe has to be larger than zero, correct? Now, you may have a process that perfectly could be a changing entropy that is negative. You can have the system, the entropy of the system, the changing entropy of the system could be less than zero. You can still have a process that is spontaneous. It just means that the changing entropy for the surroundings has to be larger, okay? Once we start talking about phase changes and entropy, this is going to be a little more clear. But for now, the thing is that if you have this case that the entropy of the system, the changing entropy of the system is negative and the changing entropy of the surroundings is positive, then if the changing entropy of the surroundings is positive, you will end up with a changing entropy for the universe larger than zero. Okay? So let's put it this way. If you have this condition, okay, a negative changing entropy for the system and a positive changing entropy for the surroundings, if the absolute value of this is larger than the absolute value of the changing entropy for the system, and let's take this down here. Okay, if the changing entropy, the absolute value of the changing entropy for the surroundings is larger than the absolute value of the changing entropy for the system, then you are in this condition. The changing entropy for the universe is larger than zero, and that will be a spontaneous process. Now, how can we picture this disorganized state, those ways to dissipate energy? I mean, how the other way you can see this is how many different ways can you represent a system, okay? Those different ways have to be equivalent. That therefore they will have the same energy content, so to speak. So the more ways you can arrange a system, the higher the entropy of that particular system will be. So this we're going to explain that with the example of a gas expanding in a vacuum. So here we have two chambers. Okay, we have gas in one chamber and this one is empty. So once we open the valve, what's going to happen? What's going to happen here? If we open the valve, well, you already have a picture of what's going to happen if you open the valve. But technically, if we didn't know anything about how matter behaves, then we can assume that there are three possibilities here. One possibility is that all the gas molecules stay right where they were before. Okay, that's the first step. Okay, let's say first one is nothing happened. The second state is that, well, if you have 4 particles there, all of them move to the other container or to the other chamber. Okay, so all move to other side. And then the last state would be one in which you divide those equally. Divide between chambers. And intuitively, you know that this is the most likely outcome. Okay, so this is, let's say, based on common experience or everyday life, so to speak. This is the most likely outcome, right? But now we're going to explain based on entropy why that is the most likely outcome. So we have this, right? So in this case we have, and I use color here, the book is using just numbers, but I think color makes a better impression. So you have, in the first state, you have 4 gas molecules, and then they stay exactly the same. Okay, each one of those gas molecules have their own identity, so they are the same gas molecules, but not one molecule is the same as the other molecule. So we are making distinctions between these molecules here, right? So we have 4 different molecules of the same gas. So there is only one way to arrange those molecules if the 4 stay in one of the containers. So they will stay all here. So there is only one combination, one possible combination there. And if they move to the other side, and you have all 4 molecules of gas there, then it's the same thing. There is only one possible combination. Only one possible outcome if that's the result that you are observing. Okay. Now, in the other case, when you have 2 and 2, well, this is where things get interesting, and let's expand this a little bit. So this is our initial state, right? But because you have 4 different gas molecules, then you can rearrange those molecules depending on which ones are going to transfer to the other side. Okay, so in the first state, all of them contain 2 molecules. Okay, so it's not a matter of how many molecules you have at each side, but what the identity of the molecules is in each side. Okay, so for example, in the first state, you have molecules 1 and 2 in one side and 3 and 4 in the other side. You can switch places with accordingly. So in this case, 2 and 3 and 1 and 4 on the other side. And what I want you to notice here is that those combinations are not the same. Okay, so molecules 1 and 2 in one side. In the other case, you have molecules 2 and 3. Okay, yes, it's the same gas and everything, but remember, we are keeping the identity of each molecule, the individuality of each molecule intact. So One is its own molecule, two is its own molecule, three and four. I mean, they are all different molecules. So these are different combinations, different arrangements in which you can have two molecules at each side of the those chambers. Okay, they are all equivalent because you have two gas molecules. They are the same gas, correct? At each side of the in each chamber, right? So energetically, they are completely equivalent. These are all equivalent states, okay? But if we notice in the other case, in the other two cases, there is only one possible combination when you have all four molecules, okay? These two states, this is state one, this is state two, they are different because the molecules are distributed in different sides of those chambers. But there is only one possible arrangement of all those four molecules at each side. When you only have two, then you have a total of 6 different states. Okay, they are different states because you don't have exactly the same molecules, but they are equivalent states because you still have two molecules of each one at both sides of the setup. Okay, so here you have more ways in how distribute your system, 6 different ways in which how to represent that, and that gives you 6 different ways in which you can dissipate energy through this system. So this is why the last system in which you have, once you open the valve, in which you have 2 gas molecules at each side, is the more likely outcome. And you relate that to a system having higher entropy because you have a higher number of ways to represent, higher number of ways to dissipate energy in that system. So that's basically what there is to this, okay? So this is the most likely outcome. So in a way, you can also interpret these two as entropy is not favoring. Entropy not favorable. Okay, to have those, I mean, with that valve open, this will not happen because entropy is not favorable. Okay, the entropy will force the system in a way to go to a higher entropy state, and that is achieved by increasing the number of ways in which you can dissipate the energy on that system. Okay, so it would be important for us to calculate changes in entropy. Now we're gonna enter into the domain of the chemical reactions. We're gonna calculate changes in entropy for chemical reactions. From 170, you should have done changes in enthalpy for chemical reactions, but in this case now it's going to be changes in entropy, and the calculation is pretty similar. You're going to have a final entropy and an initial entropy, so final state, initial state, and the difference between those will give you the change in entropy. Okay, if we are working with a chemical reaction, then this is going to take the form of change in entropy would be the entropy of the products minus the entropy of the reactants. Okay, and we're gonna get there in due time. Okay, so things to remember here: if delta S is positive, that's favorable for the reaction. Okay, which means the potential for that being spontaneous is high. But remember, entropy alone does not control spontaneity. You have to consider the change in enthalpy. Those together, when you have those two, then you can predict, okay, this reaction is definitely spontaneous or non-spontaneous. Okay? So how can you predict without doing any calculation how is the change in entropy for any system? Well, if you're looking at reactions, if the products are in a more random state, what does that mean? For example, gas phase. Okay, if your reaction is producing a gas, then it means it's going to a higher entropic state. That means the change in entropy will be positive, the change in entropy will be favorable to produce that reaction. Okay? So the saying goes, I mean, if you have all solids, if you have liquids, and you have gases, then you have to take a look at that. I mean, how many moles of each one you will have at each side of the reaction. That will give you an idea of how the changing entropy it is. Okay? If you have a larger number of products, okay, let's say if you have more moles of substance in the product side than in the reactant side, I mean, you are increasing the number of particles, so to speak, in the reactant side, in the product side, then you are increasing the entropy of that system. So that's another way that you can predict the delta S, the changing entropy for that system is going to be positive. Increasing temperature also increases the entropy, and solids dissociating in ions upon dissolving. Remember, that's one of the first one that we saw. You are going from a crystalline structure to something that is more chaotic. Those crystals now are all separated, and each one of the ions are surrounded by water. Okay, so you lost the order that you have in the crystal structure, and now everything is in solution. So that's a system in which you have a higher entropy. Okay, all of these situations are basically telling you that the delta S for these particular cases is going to be positive. Okay? The opposite, of course, is also true. You have a reaction in which you have a lower number of products, or lower number of moles of products than in the reactant side. That is a reaction for which the entropy is going to be negative. Okay, so these examples that you have here point the direction of a positive changing entropy. The opposite will lead you to a negative changing entropy. Okay, so that's it for now.